So let me remind us all of where we left off the last time. So we were going over structure and properties of both carboxylic acids and nitriles. I would not say they're the most closely related compounds in the world. I would say, for instance, carboxylic acids are more closely related to esters or acid chlorides, certainly, than they are to nitriles, but there is still a relationship between them. And I think by the end of class today, we'll be able to clarify that quite a bit. There's quite a bit of review in today's material. A lot of it's review for the exam, actually, so it works out really well. But I want to talk about preparation and reactions of carboxylic acids, and then preparation and reactions of nitriles. That's basically it. And based on what we just experienced in the previous section, I would say that maybe 75, 80% of today's material is review. So it's going to be very relaxing. I don't have reef pulling questions for you guys today. We just did that the other day, so I don't see any need to do it today. But please do register your attendance. We're taking attendance via reef. Good. So what are some ways that we know of to make carboxylic acids? Well, we know quite a few, and we're about to learn one new one, and even really it's not all that new. So we already know that you can take an alkyl benzene, which may or may not be substituted with one or more other groups on there. Again, remember this abbreviation means whatever Y is, we're going to stick it somewhere on this benzene ring. And it doesn't matter if it's orthometa or para to the carboxylic, or rather to the alkyl carbon. But it's a reaction of alkyl benzenes. And I'm getting conflicting results on this, actually. Some of my sources are saying that the carbon has to have at least one benzylic hydrogen. So I happen to think, even if there is no benzylic hydrogen, you treat it with permanganate ion, man, that's one of the best oxidizing agents known to man. I think it would still find a way to chew it up. But be that as it may, whether or not you need that benzylic hydrogen, the benzylic carbon certainly gets converted to a carboxylic acid. And any and all other carbons, if any, that might be attached to that carbon in the original alkyl group, those get chewed up and spat out. Those wind up as molecules of carbon dioxide. But certainly the only organic product will be the corresponding carboxylic acid. So that's the fate of the benzylic carbon. And there you go with that horrible word again. Remember, benzylic means next to a benzene ring. So basically it sounds like church beetle. You see, that's just it. I kind of think it would. I mean, it may take longer, it may take more heat, but I kind of think it would. I still think you'd get benzoic acid. I don't know. I've seen both, but I guess I've never really done one of those reactions, so I couldn't really speak to it from personal experience. But again, permanganate ion is one of the best oxidizing agents there is. It's right up there with dichromate and all these really crazy oxidizing agents. So I have my doubts that that's true. Maybe we should play it safe and act as though it's true. But I bet if you took tert-butyl benzene and cooked it hard enough in aqueous alkaline permanganate, I think you'd still get it. Whether or not that's true, one thing I do want to point out is I think you'll find at least 90–95% of the time, whenever we use the permanganate ion, it's done in alkaline solution. The permanganate ion seems to like things alkaline, unlike the chromate ion, which likes things acidic. That's why we need this aqueous acid workup. That's required, because otherwise, as soon as we generate our carboxylic acid, it's going to get deprotonated by the base. So we do need to work this up with aqueous acid. The first action of the aqueous acid will be to neutralize any leftover hydroxide ion, and then it will start putting the protons back on. And we'll go from CO2 minus to CO2H. So that's important. This does require an acid workup since we're under alkaline conditions. In fact, we're going to see that idea a couple more times at least, just in today's lecture. And we won't be done after that. That's going to be pretty common for reactions done under alkaline conditions to require an aqueous acid workup. So point being, that's one way that we know of to make carboxylic acids. If you've forgotten about that reaction, it's in chapter 16, so you can review that. I've tried my best to give where to look back if you need to review anything. I'm pretty sure all of this is also in your class notes, but I've tried my best to be specific about that. So that's one way of making carboxylic acids that we know already. Another way that we know already comes from back in chapter 17. And we also touched on it recently in chapter 19, which, by the way, is in this unit for the exam. The syllabus always says when the exam is and what's going to be on the exam. So, so what we said back then was you could take either a primary alcohol or an aldehyde. Both of them can be oxidized. And the way we do that is with aqueous acidic chromium-6 reagent. This is also sometimes written H2CrO4 chromic acid. It's the same thing. I think you can see for yourself, if you add H2O to CrO3, you get H2CrO4, right? So that it's the same reagent. And occasionally they'll mention this being done in a solvent. If we do use a non-aqueous solvent or a solvent in addition to the water, you want that to be something that's not going to react with the oxidizing agent, something like, say, acetone, which cannot be oxidized further. So certainly you wouldn't want to use anything oxidizable like an alcohol because, that'll react. So be that as it may, the product is going to be whatever is the corresponding carboxylic acid. And again, by corresponding, I mean that it is the same number of carbons as the starting material. And it also bears mentioning that if you start with a primary alcohol, it will turn into the aldehyde during the course of the reaction, but it won't stop. The aldehyde will get oxidized again, and you'll go up to the carboxylic acid. And if you review in chapter 17, which might be worthwhile to do, you'll find, what if you wanted to oxidize the alcohol to the aldehyde and stop, not go any further, not go up to the carboxylic acid? You can do that too. That uses a milder oxidizing reagent, such as PCC, pyridinium chlorochromate, or DMP, desmartin periodinane. So either of those will oxidize a primary alcohol to an aldehyde and no further. It stops at the aldehyde. But if you use a stronger oxidizing agent, like essentially chromic acid, also called Jones reagent, by the way, there you go, everything has multiple names, but Jones reagent will oxidize either of those guys up to the corresponding carboxylic acid. We talked about that in chapter 17. Another way we have to make carboxylic acids is by hydrolysis of nitriles. So if you heat a nitrile in dilute aqueous acid, you will wind up getting the corresponding carboxylic acid. So the carboxylic acid carbonyl carbon used to be the nitrile carbon, and the nitrogen in the nitrile winds up in a molecule of ammonia, or again, technically in an ammonium ion, NH4+. Either way, it's going into the aqueous layer and then into the waste jug. So we are not responsible for the mechanism yet. We will get to that mechanism and the mechanism of other similar reactions in chapter 21. So we'll get there. I should mention, we'll also learn in chapter 21 that you can also do the reaction in aqueous base. So instead of H3O plus in heat, H2O hydroxide in heat. Then, just as before, you would also need to do an aqueous acid workup. And we'll talk more in detail about that in chapter 21. But I just want to point out that this reaction works either in acid or in base. But these reactions that occur under alkaline conditions, it's commonplace that we'll need to do an aqueous acid workup in order to neutralize the base and give us our free carboxylic acid out, so that we're not stuck trying to isolate a carboxylate ion, which is rather difficult. So far, so good. Those are three ways that we essentially already know of to make carboxylic acids. We've mentioned hydrolysis of nitriles before. So everyone pretty much grasping all that. Another method of making a carboxylic acid, which is new, but then again, not really new, is by reaction of either a Grignard reagent or an alkylithium. Except instead of treating the Grignard reagent with an aldehyde or ketone or an ester, as we did in chapter 10, so if you want to review about these types of reagents and their reactions, we covered that in chapter 10. And also to some degree in 19, we talked about that a little bit. But be that as it may, any Grignard reagent or alkylithium reagent, instead of treating it with an aldehyde or ketone, of all things, will treat it with carbon dioxide. And actually, someone in your previous class, or the class previous to you, told me you're about to do that in lab, maybe next week. So in fact, I think you're even using CO2 as an electrophile, and some were of the opinion that you're using dry ice, which is interesting. Careful handling the dry ice. It's un poco cold, like colder than the winter storm we just had. But I thought that you could also do that by bubbling CO2 gas into the reaction mixture, which admittedly is kind of a pain. You got to get a gas cylinder and all that stuff. The only worry I would have with using dry ice is, as you may be aware, dry ice is anything but dry. There's always some water in it. But if that's true, if you're actually using the dry ice, then that tells me that the reaction of the organometallic reagent with CO2 is faster than the reaction of the Grignard reagent with water, which is plausible. I can well believe that. In any case, you then get out of this not the corresponding carboxylic acid, you get the chain homologated carboxylic acid, which is a $60 way of saying that it has one more carbon than what you started with. And this Grignard reagent or alkylithium could be something given to you. Someone told me in your case, they're going to give you the Grignard reagent, which is very nice of them. I'm sort of, usually we of the students make the Grignard reagent. It's a good experience, sometimes a little bit frustrating, but well worth the effort, I think, in which you will learn that making a Grignard reagent, and I've made many a Grignard reagent in my life, it's part science and part art form. So there's both aspects. But be that as it may, you wind up getting the chain homologated carboxylic acid. The mechanism, I don't think, will surprise you. And again, you might be given a Grignard reagent or alkylithium. If not, you can also make it from the corresponding alkyl halide. So that's a reaction we know about already from chapter 10. But if we treat an alkyl halide of this type with magnesium metal and diethyl ether, that's the art form part. It will insert magnesium and you will get the corresponding Grignard reagent. Or if you wanted, you could treat the alkyl halide with an excess of lithium metal, another diethyl ether or hexane or pentane or something, and you will then get the corresponding alkyl lithium. Truthfully, if I were doing something like this in real life and I had the choice, I would try the Grignard first, because if the Grignard isn't one that I can just buy, in my experience, at least with my hands, you know, and every chemist is different, but in my hands, I found it much harder to make the alkylithium cleanly than to make the Grignard reagent. So given the choice, I would use the Grignard reagent. But if you're given an alkylithium, that will certainly work. And you guys may be given the alkylithium. Either will work. They're interchangeable. Once you have that Grignard reagent, whether you make it or are given it, then you add the CO2, and we're familiar with that reaction. The electrons in the carbon metal bond, whether magnesium or lithium, are going to stay attached to the carbon, right? It's going to react like a carbanion, and that will attack the central carbon of CO2, just like it would attack an aldehyde or ketone. And as you'll see, you'll get the carboxylate ion. And that carboxylate ion will swim around quite happily until you add aqueous acid. That will first destroy any leftover Grignard reagent or alkylithium, since those are very reactive and we need to kill that off in order to isolate our product safely. And then it will put the proton back onto the carboxylate ion so we can isolate our free carboxylic acid. So Even though this is technically a new reaction, really in many ways it's not. It's just an application of what we already learned in chapters 10 and 17 and 19, where we talked about using Grignard reagents to attack carbonyl groups. So that's basically that. Good. So these are what, 1, 2, 3, 4, wait, 1, 2, 3, 4 ways that we know of to make carboxylic acids. Almost all of which is reviewed. So far, so good. Any questions so far? Or don't tell me I did it again and that was so clear and I'm such a wonderful teacher that no questions were even possible. Your minds are so flooded with the light of truth that you're just flabbergasted by the brilliance of the thing and you don't know how to, okay. Oh, what happens to MGBR again? Good question. Well, there are always inorganic side products and you'll wind up getting magnesium salts. I would expect you'd get either magnesium hydroxide or magnesium bromide or a mixture of the two. Either way, it's going to be an inorganic salt that's going to be water soluble. That goes into the waste jug. Same thing if you would, the alkyl lithium, by the way. You would make either lithium hydroxide or lithium bromide or chloride in the end. That's going to be gone. That's going to be separated from your organic compound during the aqueous organic extraction and will wind up in the waste jug. No, it's a perfectly good question. I'm relieved that I'm not such a good teacher that no questions were possible because I find that very hard to believe. Good. Other questions then. Can't you also do oxidative cleavage with alkynes? Yes, that's a good point. That if you treat an alkyne with ozone, yes, you'll get carboxylic acid functional groups. So there might be other reactions like that as well that make carboxylic acid. This is not an exhaustive discussion, but there's other ways of making carboxylic acids too. What Faith is talking about is, let me clear myself some space over here. That if you take an alkyne, and honestly, if it were me, I would choose a symmetrical alkyne. And you treat this with ozone in dichloromethane solvent. Then I would expect that you would get 2 molecules of the corresponding carboxylic acid. So you'll get 2 of those. It will cleave the alkyne, depending on who you had for organic 1. If you had me, then the way we described this reaction was, let's see, a line, bottom edges, I'm just picky. Then the way we described this reaction was your first step, just as with alkenes, is you take your scissors and you cut multiple bond. But where we had an alkene, we would then use our oxygen tweezers and stick oxygens on those 2 broken ends and get aldehydes and or ketones. In this case, instead of using our oxygen tweezers, we need to use our Harry Potter carboxylic acid spell magic wand. And we'll cast the carboxylic acid spell on both of these formerly alkyne carbons and turn them into carboxylic acid carbons. So we of course didn't go over the mechanism. But yeah, that's another one that we also know. It's helpful to know these things for synthesis problems, for example. The more reactions you know, the better. So good, so everyone comfortable with making carboxylic acids? Oh, one last thing on this. You see why I really think it only makes sense to do this with a symmetrical alkyne. Because if it's not symmetrical, then you'll get, instead of 2 molecules of the same thing, you'll get 2 different molecules, and I don't see the point of that. You get kind of a big mess. Good. So now that we have our carboxylic acids, what can we do with them? Well, there's a few things. again, which if we didn't know them already, at least I don't think are going to be a big surprise. So we already know that carboxylic acids can be deprotonated with even a moderate base. And sure, you could use hydroxide, but you don't need a base anywhere nearly that strong. It'd work, but you don't need it. I mean, let alone something stupidly strong like butyllithium. You don't need to go that far. Even the bicarbonate ion is a more than strong enough base to deprotonate a carboxylic acid. And the way we know that is by the relative pKa's. So carboxylic acids in general, I think you'll find in the absence of other functional groups, generally their pKa's are round and about 4 or 5, somewhere in that general time zone. And of course, the bicarbonate ion, I should know the pK of carbonic acid off the top of my head. I feel like it's around 8, something like that, 9. Anyway, acidic enough that or weakly acid enough that the conjugate base, the bicarbonate ion, is a strong enough base to deprotonate the carboxylic acid. And so once you have that carboxylate ion, one of many things you can do is to use it as a nucleophile in an SN2 reaction. It's not the only thing that you can do with that, but it's one of the things that you can do. And this is actually a way of making esters. So if we deprotonated, let us say, benzoic acid with aqueous bicarbonate, and then shot in some 1-bromopentane, I expect that we would get the pentyl ester of benzoic acid, pentyl benzoate. And mechanism shouldn't be anything astonishing for us at this point. By the way, that's one thing you notice about the second semester of organic chemistry. The further we go in the semester, the less able I will become to surprise you. The more everything just becomes same old, and something we've seen already. But so here's your bicarbonate ion. That's a more than strong enough base to deprotonate our benzoic acid. That benzoate ion, then once we add the 1-bromopentane, will attack that primary carbon. Again, for best results for an SN2 reaction, you want your alkyl halide or alkyl tosylate to be primary. Secondary might work. I don't know that you'd necessarily get the greatest yield in the world, but it might work. So that, of course, kicks out the halide. This is an SN2 step. So if you need a review about SN2 reactions, you can do so in chapter 11, and that will give you the ester. And just as someone asked before, perfectly reasonable question, of course, there's inorganic side products as well. I would expect you'd get things like sodium bromide, for instance. Once you protonate the bicarbonate ion, you get carbonic acid, H2CO3. That's actually pretty unstable, tends to break up to form CO2 and water. So you might see, I'm sure you would see bubbles of CO2 gas coming out. And by the way, that whole equilibrium involving carbonic acid, the bicarbonate ion, the carbonate ion, CO3 2-, and also carbon dioxide and water, that whole thing is going on in our lungs right now. That's a natural part of respiration. That's why we breathe out carbon dioxide. So that occurs quite naturally. So you get that thrown in for free, no extra charge. Good. Any questions on that? We're doing, again, reactions of carboxylic acids. This is one of them. They can be deprotonated by even a moderate base. You don't need a strong base at all. And one of the many things you can do with carboxylate ions thus generated is you can do an SN2 reaction with them, use them as the nucleophile. So everyone comfortable with that? Seems still a bunch of people have, well, maybe not. I think a bunch of people clocked in and then left because this says 81 and that says 71. That's fine. Good. Well, let me switch to the next page and we'll continue on with reactions of carboxylic acids. One that we learned last term is that carboxylic acids can be reduced with lithium aluminum hydride. And so, but we didn't really cover the mechanism, and I don't think we'll really see mechanisms of that type until chapter 21. But even without the mechanism, fairly easy to understand. You can start with pretty much any carboxylic acid you like, treat it with LAH in some ether solvent. Diethyl ether works fine, but be sure that you use an aprotic solvent here. Remember, ET2O and ETOH are completely different critters. So please be sure you get that right. But any ether solvent is fine. Tetrahydrofuran is fine. You know, methyl tert butyl ether is fine. There's always someone. 1,2-dimethoxyethane is fine. 1,4-dioxane is fine. I think you guys get the point. Any ether solvent is fine. And then we also do need a workup with either aqueous acid or even just water. That for two reasons. We first need to put on, we first need to destroy any leftover lithium aluminum hydride. That's very dangerous. And then we also need to put the proton back on the carboxylic acid. So I don't know, I would maybe want to use at least some acid just to make sure. Oh, I'm sorry. What am I talking about? It's no longer a carboxylic acid, but you do still get an anion. You wind up with RCH2O- in this reaction. And so you need to put the proton back on. So either water or dilute aqueous acid will do the job. And I think I've already told you, LAH reductions are very, very common, and they're very simple to use. I've done a bunch of them in my life, in such experience as I have in being a bench chemist. And I've already told you the way I like to work up these types of reactions is I open up the flask and pitch in little pieces of ice, little by little. The reaction is exceedingly violent and somewhat scary because you're generating hydrogen gas, which is un poco flammable. And so if there's any kind of exotherm or certainly spark, you know, it's very bad. And I always have trouble convincing students that fires are bad. They are a bad thing. They're not a good thing. They're a bad thing. But as long as they're careful, it's no problem. Once the vigorous bubbling stops, you can do your aqueous organic extraction. The aqueous layer will get all of your aluminum salts and lithium salts and all that stuff. And the primary alcohol will go into the organic layer, and they're generally pretty easy to isolate. Come to think of it, I guess we've also learned a method for reducing esters, certainly. I think it might also work with carboxylic acids, but doing a partial reduction with dival to go down just to an aldehyde. Those reactions are a little bit finicky, but it's possible, at least in principle. So that's another reaction of carboxylic acids that we know. Others that we don't quite know yet, but I want to point ahead to future chapters. In chapter 21, we're going to learn about nucleophilic acyl substitution reactions, which carboxylic acids are subject to. We'll learn about, Fischer esterification, for instance. There's another way of making esters from carboxylic acids that's, if anything, much more commonly used than the one we had on the last page. And also, chapter 22 is going to be about alpha substitution. And we're going to learn that if, whatever this R group might be, if there's at least one proton alpha to the carboxylic acid carbonyl, so on the carbon next door to that carbonyl, then we've got options. And there's things we can do to replace that hydrogen with something else. That's the domain of chapter 22. So we'll get there. That's still coming up. Good. So I don't think I need to say anything else about that. Before we get into both preparation of nitriles and reactions of nitriles, one thing I do want to point out that maybe isn't intuitively obvious until you put them side by side is that nitriles and carbonyl compounds are quite similar in terms of reactivity. And I think this is part of the reason why they're mentioning nitriles in the chapter with carboxylic acids, which are a carbonyl compound. but the two are, but carbonyl compounds and nitriles are very similar in terms of reactivity. And I think when you put them right next to each other like this, you can see why. It's because in both cases, you have a carbon atom with a pi bond to something more electronegative. So the fact that this is a nitrogen rather than an oxygen turns out not to matter a whole lot. And I actually plan to drive that point home by the end of this class today. but the two are very similar in both structure and reactivity. So nitriles have somewhat similar reactivity even to aldehydes and ketones. So what are some ways of making nitriles that we know? Well, we know of at least one way. We know that you can take an alkyl halide or tosylate, preferably primary, treat it with potassium or sodium cyanide to do an SN2 reaction. If you really wanted to put your thumb on the scale, so to speak, and make absolutely certain that we're in SN2 conditions, I think having a primary alkyl halide or tosylate will do that by itself. But if you just wanted to really press the issue, then you could use a polar aprotic solvent such as DMSO. But frankly, I don't think you even need a polar aprotic solvent. I think even in a protic solvent, this reaction would work quite well. It might just go a little slower, but I think it would work fine. In any case, you wind up getting the chain homologated nitrile. So this will have one more carbon than the alkyl halide you started with. So this again is an SN2 reaction. We talked about that in chapter 11. Since we have a little bit more time here than in the previous class, I might as well do an example of that. So what's your favorite alkyl halide? How about benzyl bromide? Not bromobenzene, benzyl bromide. Right, there you go with that inconvenient term benzyl again. So not bromobenzene, benzyl bromide is phenyl CH2. Benzyl chloride is vastly superior. You could use benzyl chloride. They're both nasty. I wouldn't use either one of them unless I absolutely had to. They're terrible lacrimators getting up your nose and horrible. Plus, could be a minor issue of benzylating your DNA, which is kind of a problem. But be that as it may, whether it's the chloride or the bromide, both of them will work. Let's say that we treated this with sodium cyanide in whatever solvent you like. It really doesn't matter. You can even use a protic solvent. Might just be a little slower, but I guarantee you it will still work. Well, I don't think this mechanism is at all mysterious at this point. Here's your cyanide ion. Again, remember, with the cyanide ion, it's the carbon that's a nucleophilic atom, right? It's a carbanion. But nothing mysterious here. That will attack your primary alkyl halide at the carbon bearing the halogen. It'll kick out the leaving group. And in this case, since I'm running out of room, I hope you'll indulge me. I'm just going to write pH CH2CN. Call that not benzonitrile, but phenylacetonitrile, I think is what you call that. I think. That's what I would call it. So, but it would work very straightforwardly. I expect you to get a very high yield of the corresponding nitrile. So, and I just used benzyl chloride or benzyl bromide as an example. I wonder why you're saying benzyl chloride is better. I could argue that either way. I think it's probably more volatile. Whether it's, I think they're both pretty dangerous. Whether it's less dangerous, I couldn't tell you. Anyway, that's one way we have of making nitriles. Works just fine. It was a dumb joke. Okay, well, I fell for it. Be that as it may, another way of making a nitrile starts with a primary amide. So you do need an amide of this type. That needs to be NH2. You can't have any alkyl groups on the nitrogen or it won't work. But other than that, it's quite general. R can be pretty much whatever you like, as long as it's, you know, sturdy enough that it will withstand one of these ridiculously reactive dehydrating agents. And I anticipate that you could use either thionyl chloride or phosphorus oxychloride. They're both really, really strong dehydrating agents. Reason being, and this will help you to remember them, reason being, if you add water to either of these, you will get a violent reaction and you will get either sulfuric acid or phosphoric acid, respectively, plus HCl. So these two compounds love water, and they will suck out the water wherever they can find them. That's why they're really, really bad to get on your skin, because now they're sucking out the water from your skin. So you get pretty bad burns that way. P2O5 is another excellent dehydrating agent. I would expect that would work just as well. So yeah, P2O5 is fine also. I'm saying benzene reflux. I don't know that that's the only solvent you can use. That's the one I'm given at this point. But refluxing, of course, is fancy term for boiling. And the reason refluxing benzene is particularly nice is because if you set up your glassware with some particular tools, you can remove the water that you would get, insofar as you can ever get it away from the thionyl chloride and the phosphorus oxychloride, of course. But benzene is nice because it's unreactive. You don't want to pick anything that will react with the phosphorus oxychloride or the thionyl chloride or the P2O5 for that matter. So you want something quite inert. In any case, you wind up getting from that the corresponding nitrile. You're not responsible for the mechanism, but I think you can see how this works. There's two hydrogens on the nitrogen plus the carbonyl oxygen. Those are going to get taken out to form a water molecule. You get the elements of water right there. So you wind up then getting a triple bond between the carbon and the nitrogen. You dehydrate the primary amide and you get the nitrile. So it's another way of making nitriles. We'll eventually, again, get to mechanisms somewhat like this, I think, in future chapters. But I'm not real concerned about the mechanism just now. So now we have two good ways of making nitriles, and I've got about 10 minutes left. I think there will be plenty of time for that. What about reactions of nitriles? Well, we already know some of them. One of them I just mentioned earlier today. We know that you can hydrolyze a nitrile to form a carboxylic acid. We'll learn more about that reaction in chapter 21. That can be done under either alkaline or acidic conditions. And just to prove to you that we said it earlier today. Oh, did I delete that in making another one? Oh, yes, it was here, but I got rid of it to talk about alkynes. So I can't exactly prove it. But we did talk about that earlier today. So that's one thing you can do with nitriles. Another thing you can do with nitriles, we talked about back in chapter 24. We said that you can reduce a nitrile to form a primary amine. And I was running out of time in the previous class, but I've actually got time here to discuss, at least to give an example of that. So we might as well do that. Lithium aluminum hydride is a very good reducing agent. And so, why don't we take the nitrile that we just made? CH2CN, phenylacetonitrile. Well, if we were to treat this with lithium aluminum hydride, so usual conditions, first step, LAH, in some ether solvent. If I had a choice, I would just pick diethyl ether. It's cheap, it's easy to get, and it's very easy to get rid of also, because you want to get rid of your solvent at the end. And diethyl ether boils at somewhere between 35 and 40 Celsius, I think. So it's very easy to get rid of. And then you're going to want either dilute aqueous acid workup step or water. I might actually favor just using plain water here. See if you can figure out why. but from this you get the corresponding primary amine. So it will have the same number of carbons as the nitrile had. So this CH2 is the benzylic CH2 that was there to begin with. This CH2 here used to be the nitrile carbon. And of course, the nitrile nitrogen winds up in the primary amine. So lithium aluminum hydride will reduce a nitrile to, again, the corresponding primary amine. Corresponding, again, meaning it is the same number of carbons. We're going to talk more in detail about mechanisms like that, although we've already had something to say about mechanisms of that type in chapter 19. And I don't know that I'm really concerned that you're very familiar with this exact mechanism, but I hope, at least by the end of class today, to establish to you that the mechanism is not surprising of reactions like this. I would say that the two hydrogens on the carbon come from the LAH, and the two hydrogens on the nitrogen come during the aqueous workup. And I would, remember I said how I would want to use water rather than H3O+. I would not want to let this get too acidic because that nitrogen on the amine is quite alkaline, right? And if you allowed the solution to get too acidic so that you protonated that nitrogen, that's now going to go into the aqueous layer. So I would want to lay off in the acid with this one. I would want to keep it neutral to even slightly alkaline, just to make sure that we can isolate our amine-free base. Good, so that's another reaction of nitrile. We talked about that in chapter 24. So chapter 24 is part of actually this exam's unit, so it bears repeating. And then, last but not least, you can another reaction of nitriles is with a Grignard or alkylithium reagent. And then, of all things, you wind up getting a ketone out of it. So the portion of the ketone that has the carbonyl and R1 comes from the nitrile. So the carbonyl carbon used to be the nitrile carbon. And then the other group, R2, comes from the Grignard reagent or alkylithium. And we'll have more to say about reactions of this type, I would say, in chapter 21, but I do want to point out that, I mean, at first you think, wow, where did we get the oxygen from and where did we get this carbonyl from? I just wanted to show you that it's not all that crazy. And I think we'll have time for me also to do an example of this type of reaction. But again, we've already established back up here, until I deleted it. Well, be that as it may. We've already established that nitriles are like unto, that nitrile carbons are like unto carbonyl carbons. So no big surprise there. And just as we have nucleophiles adding to carbonyl carbons, especially such as in aldehydes and ketones, that was in chapter 19, well, small wonder that they can also add to a nitrile carbon, and you'll get an intermediate of this type. And that's what this reaction is all about. The Grignard reagent just attacks the nitrile carbon. And so you get at first an intermediate like this, where the nitrogen is a minus charge. But then once we acidify, once we do our acidic workup, you're going to add the proton back onto the nitrogen, and then you will hydrolyze the resulting imine, because NH, that's an imine. And we talked about that in chapter 19. And that mechanism is exactly the same as formation of an imine, except exactly backwards. It's just the reverse of imine formation. And so from there, you get your ketone out. So let's maybe do an example of this. Well, since we've already got our phenylacetonitrile, let's say that we treated our phenylacetonitrile with, what Grignard or alkylithium? How about isopropyl Grignard? Now someone's going to say whether they want the magnesium chloride or the magnesium bromide. Jokes on all of you, I'm going to make it the magnesium iodide. So there. I'm just teasing you. And of course, we'll want some ether solvent, preferably. Probably the Grignard reagent itself is going to be, I think that's one you can buy commercially. And I expect it would come in solution, either in diethyl ether or THF. So once you're done with that, we'll do our aqueous acid workup. I don't think we have any amines here to worry about protonating. So I would expect that what we would get out would be, okay, CH2, C double bond O, and then the isopropyl group. So I would expect that we would isolate this ketone out of that reaction. So again, it goes by the Grignard reagent attacking the nitrile carbon. So at first we'll get C double bond N minus, and then, and that's actually what's going to be swimming around quite happily in solution until we acidify. Once we acidify, first we put the proton back on this anion and get NH, and then also the acid will hydrolyze the imine. So it will be the same mechanism as the imine formation, except backwards. It's that same reaction mechanism, but in reverse. And you'll wind up getting, I guess, a molecule of ammonia, which winds up in the waste jug, and this ketone. So that's what I would expect we would get out of this reaction. Good. I can't really think of anything else. There's only 2 or 3 minutes left, so I don't know how much review I can do in that time. I'm sure I owe you at least that much from past classes and going over. Any questions about preparation or reactions of nitriles? While you're thinking about that, on Monday, we will cover chapter, I think it's 27 on lipids. That, of course, will not be on exam number 2. That'll be in exam number 3. But you know me, I like to have that slop day in between, just in case there's another winter storm or other act of God or something happens and we have to cancel class. I just feel safer doing that. But we'll cover that on Monday. That will not be a very deep or challenging chapter, I don't think. It'll be pretty relaxed like today was.